So first example is a follow-up. Well, actually, I was planning on doing the example anyway, but it is sort of a follow-up in terms of the questions that you guys asked previously, which is, well, what happens if you have multiple sources and multiple sinks? So this particular network is dealing, just a second, trying to find my, there it is, trying to find my cursor. All right, so this network here, you can think about it in several different ways, but in terms of where it was pulled from like a supply chain, okay? So for example, over here, these guys, and I realize now that I probably should make them a little bit bigger, so let's see if we can't highlight them slightly. I really don't want to highlight them in yellow. Let's see if I can highlight them in a color that matches a little bit better with the graph. Wow, that's a terrible color. We're going to go with it anyway. So those guys there, the vertices labeled with B, C, and D, would be the guys that have a certain amount of supply. So if we're looking at some sort of supply chain, this could totally be modeled in like an economics type situation. You could think of these as like companies or warehouses where where you have stuff. Pick your favorite thing that they have, either to sell or to supply in some way. So in terms of your units, this guy here has 60 units of supply. This guy at vertex C has 40 units of supply. This guy at vertex D has also 40 units of supply, whatever it is that these guys are holding. I personally have a tendency to picture these as warehouses, but that's me, okay? Now on the other side of the graph, and let us find a slightly less obnoxious color. Nope, that one's going to be super obnoxious. But at least it's not as much of an issue as the yellow highlighter is. I'm trying to make something that pops out but doesn't completely draw attention. I don't know that we succeeded there. All right, so on the other side here, vertices H, I, and J, they have demand associated with them. I, in my head, picture these as like stores, and they are trying to buy stuff from their warehouses. So what do they want? They want vertex H wants a demand of 50, or it wants 50 units of whatever it is that we're talking about moving across this network. Down here at vertex I or store I wants, or the official term is demand, wants 40 units of whatever the thing is that we're trying to push through this network. And for vertex J, their demand is 40 as well, okay? Now, in this type of a network, if we were actually in an economics class, which here we are totally not, but if in this sort of situation, if you were actually modeling the actual real-life scenario, what would happen? You're looking here at, you're trying to meet all of the demand of all the stores. You want to be able to fill all of their orders, and we want to divide that up from each of the warehouses. Notice here, at first glance, you might think, hey, ship all of the 40 amount of supply from vertex C straight over to vertex I or store I. Same deal with warehouse D. Maybe you ship it all the way out to store J. They have 40. These guys over here want 40. And then up here, you've got a supply of 60 and a demand of 50. Ship it straight out. Now, there you go. That's also another way to think about that. So in terms of this guy, notice if you only look at the supply side and the demand side, it looks like you can easily meet all of your demand, which is the goal of these type of questions if you have a supply and a demand. But if you actually look in at the network, the weights attached to each of these directed edges would be like, if you're thinking supply and demand, this is often shipping routes. So this would be the edge might represent the shipping route. So you'd have something like if you're shipping via trains or via trucks or whatever it is, maybe this is the route that they have to take. Maybe this here, your vertex, like vertex E, let me actually make my cursor a little bigger. So here at vertex E, this might be where your shipping lines split off. So maybe this first line is you're going to use a train, and then when you get here to vertex E, you're going to put the containers on a ship. Why would I say ship? I don't know. Truck is what I was actually thinking in my head. But you could do the same thing with ships, etc., or planes, okay? But notice here the weights themselves correspond with how much of whatever your item is that you're trying to ship would actually be able to go across the edge. So maybe this weight corresponds specifically to, if you're dealing with a truck, how much the truck can actually be loaded up. Okay, so those were where some of these edges and weights would come from if you have a quote-unquote real-life situation that you're modeling. Okay, now for us, we don't have to worry about any of that, or I'm not going to bother worrying about any of that. In terms of what we've got here, notice that these highlighted guys, the ones in that sort of weird orangish color, they've got a supply. So these warehouses, what does that mean? That means you've actually got a supply coming in. So these guys would all be considered sources. Now, remember what we had for our definition of a source. There's no issue whatsoever at vertex B, but I'm claiming that vertex C here is also a source. Why should you have a big flashing warning sign come up in your head if your head actually had warning signs? Exactly, because vertex C and also down at vertex D that I'm also going to claim as a source, both of those guys actually have degrees or edges coming into them. So technically speaking, those shouldn't be classified as a source. Now, anybody have a guess on why we have to classify those three vertices of B, C, and D as sources? It's not the out degrees. It's also not the in degrees. It's something we didn't have in the graphs last time. You got it, it's the supply. So sources is where new stuff, notice the word is very vague there for stuff, that's not a technical term. Here, these supplies is where you've got new stuff coming into your system. So that's what a source is. It's where you've got new stuff coming into the system. So we've got a conflict here. We've got well, okay, not at vertex B. It's a source in all definitions. But for vertex C and D, we've got a conflict in terms of it being a source that has to be a source because we've got a supply attached to that vertex, but it not fully meeting the criteria of a source like we've done previously. Okay. So in terms of dealing with this, we're going to do an adjustment. And what we're going to do is we're going to adjust this side of the graph, vertices B, C, and D, in such a way that we get two things. First thing is we're going to adjust it so we actually take care of the supply like we need to. But we're also going to adjust it so we actually have a source by the technical definition that we need, meaning no in degrees, okay, or our in degree is 0, so no edges coming in. We also have a similar issue over on the right side of the graph. These guys highlighted in that horrible purple color. I'm regretting that already because I have to look at it. Here, these guys I'm going to claim all have to be labeled as sinks. Okay. Now, there's no problem with vertex H. That guy is totally a sink by all definitions. All of the edges are coming into vertex H, but vertex I and J have a similar issue that we had with our sources. You've got here an edge that is leaving both vertex I and J. Anybody have a guess on why we still have to tag vertices I and J as sinks? Yep, again, it's that same issue. It's the technical term is the demand, but I like your description that one of you sent in is those vertices are going to remove supply. Yeah, you've got this issue going on. So we're going to adjust the supply side or the highlighted vertices B, C, and D. We're going to do a similar adjustment on the demand side or our vertices H, J, I, and J. And I am now totally regretting not copying that exact same graph down, so we'll freehand the whole thing. It'll probably look better anyway because I'm going to draw it in black. Okay, so here's the fix. You take the exact graph you currently have, but we're not going to write out to the side here the supply and the demand with the side. Okay? So we're just going to copy this part out, and I really, really, really don't want to have the highlights, so we're not going to highlight them in the next one. Okay? So here we've got B, we've got C. Why did I not just draw a straight line? D? And there's a grand total of, what is that, 9 vertices, if I made my count correctly. and then a bunch of diagonal edges. And all of these have direction. We'll go back in and put in the direction. But let's label the vertices first. There's H, there's I, there's J. I'm missing interior ones, so there's F, there's G. Let's put in the directions. Horizontal ones are nice. Vertical, go down, then up, and horizontal always go top down. All right. So the only thing missing are all the weights. So let's put in all the weights. All right. So we've got a weight here of 50, 50, 30, 30, 30, 30. Trying to do it strategically so I don't miss any of these guys. 30, 20, 40, 30, 30, 40, and it should be only diagonals that I'm missing. So we've got 20, 30. These weights aren't going to matter because we're not actually going to solve this problem. Just illustrating how to adjust. All right. Whew. Here's how to adjust. We're going to get one source. Here's our new source. We're going to call it A. We're going to have one sink. We're going to call our sink Z. Now, what this does is when you put in a new source and a new sink, all of the guys who were before tagged as sources or sinks, regardless of whether they look like they match the definition or not, are no longer going to be sources or sinks. So here's what you do. Everybody that had to be a source, just because it had the supply coming in, regardless of whether the direction of the directed arrows was going the right way or not, we're going to connect to our new source. So A to B, A to C, and A to D. And those are the only lines right there that are coming in and connecting. I'm going to highlight this in orange, highlight it in orange, and highlight it in orange. Okay. Now, because this is a network, all of your edges have to have weights. Any guesses what the weights should be on those new edges, AB, AC, and AD in top to bottom order? Yep, this is where you put the supply, okay? So our supply, we're supposed to bring in 60 to B, so we'll put a weight of 60 right here. We're supposed to bring in 40 units to vertex C, so we'll bring in 40 units to vertex C. And lastly, for vertex D, we're supposed to bring in 40 units. Notice now you're entering in or you are dumping that new supply of whatever product or otherwise it is that you're picturing in your head in at vertices B, C, and D, just like you wanted to with what we tagged just as supply before. But we now have, according to our definition of a source, a proper source in the graph theory sense as well. That means we'll be able to use our graph theory properties, theorems, algorithms, etc., to be able to solve this thing. Okay. Turns out same adjustment happens with respect to the sink. Should still be drawing in black. Nope. So here, you connect a directed edge between your new sink and everybody who had to be acting like a sink in the original network. So we'll have H to Z, we'll have I to Z, and we'll have J to Z. And notice here the direction, because you're building your new sink, it has to be going into your sink. Now go ahead and color code this one as well. I won't be able to do that horribly obnoxious color purple, and I'm not seeing one that's super close. So I'll break down and do that weird pink color. Although there's no way we're making it that fat. So those are our newly added edges right there. Now, remember it's a network, so we have weights in all of our edges. Any guesses what the weights would be on HZ, IZ, and JZ in that order? So again, these would just be the demands. So 50, 40, and 40. Okay. So this is a standard adjustment that you do, and what it basically says is you didn't draw your original network correctly, this is the real proper graph that you should have originally drawn to model the situation that you have. Okay, so this is actually a standard practice that you do with, actually you can do it with a bunch of different types of graphs depending on what it is that you need to do. Okay. And the reason for doing that is the new network with the single source and the single sink is modeling exactly how your supply or your items, whatever it is you're picturing in your head, actually move through the system. Okay? So if you want to think about vertices B, C, and D as like warehouses, this source A maybe is the manufacturing plant that ships it to the warehouses, if you want to think about that in your head. Over here, if we were thinking of the original pseudo sinks, vertices H, I, and J as like stores, you could think of the real sink that we forced on here. Maybe you could think of that as like your customer base if you want. Okay. So in terms of adding the one source and the one sink, this is a technique that you use anytime you have multiple sources, multiple sinks, or like in this example, multiple pseudo sources and pseudo sinks. Okay. Ooh, and let me put a little bit more space here for our next example. So that's the classic fix. Now, next example is actually dealing with a definition and an example of how to work with that definition in an example. So we've actually talked about a cut set before. So this here is actually very similar to, actually it's exactly a cut set. So if you look at a cut, what it is you take some collection, some subset of your vertices from your network. So V here represents the set of all vertices in your network. P is some subset of those vertices. Okay. The complement of P is all the vertices in your network that were not in your originally tagged set of vertices, capital P over here. Okay. So then in terms of symbols, you've got this ordered pair of P, comma, not P, or the complement of P. And this is, your book represents that as the set of directed edges, where the directed edge does the following. And let me do a little picture over here to the side. And let me do it in a different color. So if your network looks roughly like this, you've got set P, you've got set P complement, then all of the edges that are this XY edge, you've got an X in set P, and the directed edge goes over to some vertex Y in set P complement. Okay, so that's the idea here. Your book actually for directed edges always puts a little arrow over top. We haven't been, we've just been using the parentheses right here. Same deal. Okay. Now let's see how that would occur if you're actually looking at some network. So here's a prepped up network. Roughly speaking here, we've got somebody that looks like a square with two diagonals through it, and then you've got what looks like two triangles on the side. So suppose you pick an arbitrary cut. So I'm just going to pick an arbitrary cut here. I'm just going to do this. Okay. So that line is symbolic on the graph to indicate your cut. Notice if we were trying to deter, when we were back looking at disconnected graphs, we were able to put lines through our graph and make it so it never crossed any edges. If you actually have a connected graph, any line you put in here, as long as there's at least one vertex on either side of the line, is going to cross some edges. Okay? So if we wanted to apply this same terminology to the cut that I just arbitrarily put through the graph right here, and you can put the cut wherever you want, what would we have? Well, classically speaking here, you pick one side of the cut, this line in black right here, to be your set P. I'm going to pick this side on the left right here because that's going to be standard for what we're going to do in this picture, is left side being P, but you can actually flip-flop it. So in this case here, the vertices on the left side of this black line that represents the cut are vertices A, B, and C. So P complement would be what? What do you guys think? Don't overthink it. It would be the remaining 3 vertices, D, E, and Z. Oops. Do not close a set with a parenthesis. It doesn't work well. That's literally it. That's all you do for finding your P and your P complement. You literally, one of the sets is the vertices on one side of the cut, the other is the other one. Now, if you actually want to represent the cut, the order in which you put the P and the P complement matter. So these are the directed edges that are crossing this cut right here. Okay? So if we write down these directed edges, we have who? Well, we have BD, and I'll go ahead. Wow, I can't write a B or a D today. Start over. We've got BD, and if we do it the same way your book does, where he puts the little arrow, that's just to indicate for sure you're definitely using a directed edge. So we're looking at this guy. Notice that is an edge that got cut by your cut. I was trying to think of a different word, but it didn't work out. So an edge that crosses that line, that black line that represents the cut. So what's another edge that you think might be in the cut? BE. Yep, BE is a good one. And again, I'll stick to what your book did. So I'll highlight this one. Anybody spot another edge? Yep, CE is in the cut. So let me go ahead and put that one in. And I'm going to claim that this cut only has 3 edges in it. Anybody have a guess why it only has 3 edges in this cut? Watch out. Yes, so the definition of a cut in a network, specifically, it actually here does, what we're doing here doesn't matter the fact that it's a network, that it has weights on the edges. What matters here is that it's a digraph underneath, okay? So all of our edges are directed. If we were in a simple graph or an undirected graph, when we looked at cut sets before, we would look at all of the edges that physically touch or cross that line representing the cut, and we would have had 4 edges in the cut set. Here, when we're on the directed graph, order matters, so it matters where your edge starts and stops. And that one edge that we didn't highlight, the edge that's D to E, notice it's starting in the wrong set. It's actually starting, this vertex D right here, is starting in P complement, so it's starting where we're supposed to be ending. So remember, let me put this in. This here tells you your edge has to start in P. So over here, this would be your P, and over here, let me just scroll up. Come, scroll up. This would be your P complement. So what that means is it's going to be some sort of subset of a cut set, like if you ignore direction. Okay, so we were definitely not going to have more than 4 edges, and then we had to see which of those 4 edges we would actually select. So these guys that you actually select for your cut are, in the future, we're going to call them forward edges. In other words, they're going in the direction we wanted them to go. This guy that we didn't select for our cut because it was going in the wrong direction, we're actually going to, in the future, call those guys backwards edges. Okay? Makes sense? Kind of okay in terms of how to read cuts for directed graphs. All right, so let us look at some more definitions, and since I wrote all the scratch work up there to the side of the graph, we got a little bit of space there. All right, so the next thing that we want to look at is, we can't see it all together, oh well. So it's something called an AZ cut. So we're actually going to look at AZ cuts quite a bit in this section, and actually in the future as well. An AZ cut is exactly what we just talked about. It's a cut, specifically this ordered pair P and P complement, but here's the part that makes it an AZ cut. where vertex A is in the first set and vertex B is in the complement. Note, in the example that we just did right here, we actually did an AZ cut. So let me actually label that here. Am I writing? AZ cut. Right there. Notice, why do we know it's an AZ cut? Because A was in set P and Z was in set P complement. Okay. Don't overthink it. Okay. Now, something to note about why we care about this is there's 2 points. First one is, if you talk about flows, and we're going to actually care about flows in this section. So remember, what did flows do? Well, all flows that went from A to Z meant we're trying to push whatever it is, material, water, supply, whatever it is we're pushing through our network is supposed to start at our source A and go to some sink Z. In other words, we're trying to go from A to Z. Any AZ flow must cross the AZ cut. In other words, it has to travel across those edges in the AZ cut. So that's the first thing. The second thing is, if we combined, or in reality add, all the capacities, and remember in terms of flows, this is using those weights. So here in this connotation, we typically use the buzzword capacity as opposed to weight. That's just the numbers associated to each of the edge. If we add all those together, not across the entire network, but just in your AZ cut, what's going to happen is we're going to get an upper bound on the flow. Now, quick check. Do you guys know what upper bound means? It is a descriptor. And this is true. You typically do upper bounds and lower bounds together, or you talk about them at the same time. So an upper bound is just, it's not exactly the same as a max, but you can think about it that way. What it says is the value of your AZ flow can't be any higher than the capacity on the AZ cut. Now remember what the flow was. The flow was the maximum amount of materials, stuff, water, whatever you want to picture in your head, progressing through the network from vertex A to vertex Z. Well, if you have to push that flow through your AZ cut, then you can't exceed the capacity on the cut or the maximum you can push through the edges on the cut when you go through the entire graph. In other words, the AZ cut is a bottleneck. And this is true of all AZ cuts. Okay? There's not just one of them, typically. Now, in terms of the next thing is something we actually talked about last time. It's in your book, Theorem 1. And what it says is if you look at any one of these flows, if you look at an AZ flow in your network, then the flow that comes out or comes out of your starting vertex A has to equal the amount of flow going into your ending vertex Z. In other words, you don't lose anything as you progress through your network. Now, there are other types of networks where you can have along the way, you start thinking about, well, maybe it's, for example, pipes and water, classic example. What if you have a leak somewhere in the pipes in the middle and you're actually losing flow? The amount of water you pump into your pipe system is more than the amount of water you're getting out at the end of your pipe system, and you need to go and track down where that leak is. So there are other situations where you can have the flow out of your source and into your sink are different, but we're not going to deal with those type of guys, okay? So we're assuming that this is a closed system and you don't have any sort of like a leak in the middle, okay? Now, Next definition deals with some mechanics. So there's something called the value of a flow. The value of a flow is its symbols, has the symbol F for the flow, and looks like absolute values around it. And this is specifically defined as the sum of the flow out of vertex A. Remember, we're leaving A to arrive to Z, or if you prefer, and this is a direct result of Theorem 1, this is the same thing as the sum of the flow in to vertex Z. And just as a heads up, do I need to worry about that? We can deal with this. That flow is always less than or equal to the sum of the capacities on all of the edges on some AZ cut that you have. Okay. Now, we talked about the capacity of a cut. It does turn out there's specific symbols to represent that we're dealing with the capacity of some cut. And it goes as follows. We'll hold off on Theorem 2 here for a second. Okay. So here, what do we have? We've got that if you want the capacity of some cut P, comma, P complement, in terms of the notation, it's the same lower letter K that represents the capacity on some edge, or the weight on some edge, that same function. But here, instead of plugging in an individual edge, you dump the symbol for the entire cut. Now, what is this defined to be? This is defined to be the sum of every single edge in that particular cut, and you add up all of those individual capacities. Okay. And since it actually goes right along with it, let's go ahead and look at Theorem 2. Theorem 2 puts these last pieces of information together and says if you've got any AZ flow and any AZ cut in your network, it turns out the value of your flow, and this is where you get that upper bound, is always less than or equal to the capacity over which you have to travel. And that gets us to most of the definitions and preliminary theorems. We've got a little bit more of them, but before we get to the rest of the definitions and theorems, let us actually do an example of dealing with capacity. Okay? So what we want to do is we want to find the capacity of some cut. We've already done an example to a cut, so let's go back to the graph that we already had, or the network we already had, and see if we can't find that capacity. And I'm going to throw that question to you guys, actually. So for this one, here's our follow-up. The part B, if you will, compute or find the capacity of our, in this case, turned out to be an AZ cut. I'll go ahead and write the symbols, but I'm going to let you guys see if you can't guess this. Don't overthink it. Don't guess it out loud yet. So we'll see if your classmates think you're right or not, I guess. All right, so I went ahead and activated this guy on Pull Everywhere. I realized the screen's got really small here, so I'm going to stop showing the Pull Everywhere screen here in just a second. I wanted to give you the URL. It's the same URL as before, and you just go to the pulleverywhere.com site. It is a little bit different than the other ones. All of our other questions have been a multiple choice question. This one is where you get to enter your own answer. Please, please, please just type the number value. So I'm going to make the graph bigger for you and stop sharing that second screen. But don't overthink it. Capacity of a cut if you already know what the cut is a relatively straightforward thing to calculate as long as you have all of those details. And when I say details, you have the full network and you know what edges are in the cut. Capacity is your buzzword for weight. So for a specific edge, these are the guys that we've in the past called weight, which is the generic term. Currently, with these type of networks, they're also called capacity. And back when we first were doing it with Dijkstra's algorithm at the beginning of Chapter 4, we also called it length. It should allow you to change your answer. Or it's supposed to allow you to change your answer if you type in something you don't like. I guess, different type of question. Oh well. All right, it looks like all but 7 of you guys have made a guess. Do the last 7 of you want to make a guess? Because I'll go ahead and show what we think the answer is, but to do that, you're not going to be able to enter in an answer after I do that. So if you want to have a guess, type in a guess. You won't have a chance to cheat the system and put in a guess after you see the answer, the correct answer choice. Just in case that was the issue with the last 4 of you not making a guess. So the last 4 of you, do you want to make a guess? Coming up on the last chance. All right, so I'm going to call time on that one and let us look to see what we think our answers are. And we'll also see if this actually displays correctly. That's always fun to check too. All right, you should now see this thing. It was supposed to come up in a word cloud, or in our case, a number cloud. So it looks like there were a couple of different guesses out there. In terms of the vast majority of you, it does look like the vast majority of you guessed the answer of 14. So let's see if that works. I'm going to stop showing you the second screen. And let us check it out. So in terms of capacity or weight, you look at the guide in the cuts, one of the reasons we highlighted it before, and you check the capacity, or if you prefer, the weight on each one of these, which would be 4 plus 3 plus 7. Where did I get the 4 plus 3 plus 7? It's the number associated with each one of those guys added up. And you should have gotten 14. There you go. That's literally it. Don't overthink it. The only thing that can mess with people's heads is if you forget any of the names involved, or if your cut is off and you accidentally either add in one too many numbers or you missed in terms of grabbing one of the capacities off one of the edges. typically those are the only things that cause people issue, okay? But this here, I personally like going ahead and highlighting these. Now, if you're having to do something in addition to a cut on your network, you probably don't want to highlight your edges at that point, but at least the first couple times if you highlight your edge, that's a nice way to see it, okay? That's it. That's all capacity is. Now, in terms of the next thing, we were where? We saw capacity, which was just the sum of all the little capacities on each edge in your cut. We saw our upper bound formula that said any capacity across any AZ cut was larger than or equal to the value of your flow. And the corollary to this particular theorem, and I only did part A of it because that's the only one that we're going to need, is dealing with, well, what's going on when you have this AZ flow and AZ cut. To go back, the question wanted to know why we didn't select this edge. That was because it was going in the wrong direction. So remember, this edge DC was not part of the edge because D didn't start in our set P here. Now, for this one, we did an arbitrary cut. So our P and our P complement were relatively arbitrary. But once your set P is selected, P complement is set, the cut is also determined by that point. Now, if you change up what your set P is, maybe your set P is only AB, you would have different edges in your cut. The key thing is the edge has to start in whatever the set P is and end in whatever the set P complement is. All right, so we were looking at Theorem 2. So corollary of Theorem 2, remember corollary just means direct results of. No is the answer. So the question that came in, and let me pull back the graph so you can see this. The question that came in was, do you have to have your set P always on the left for what we're going to use it for and apply it for in the future? Yes, we're going to have our vertex A always be inside of set P because we're going to look at AZ cuts. But in general, if you just want any old cut, it does not matter which of these two guys you actually pick for your P and your P complement. So for example, if you look at the cut, and I'm going to keep the exact same P and P complement, so suppose you just flip-flop it. Notice here the set at the beginning is now P complement, the set at the end is now regular P. So I'm not going to change these labels, but what it would mean in terms of your cut is it's no longer an AZ cut because A is not in P complement. And what it would also mean in terms of this cut, what edge or edges would be in this cut? Anybody have a guess? There's only going to be one edge, and it's the one missing edge we had from the other cut. The edge going in the opposite direction exactly. We're going D to C here. So no, there's nothing that says that starting set here has to be on the left or the right. It all depends on what it is you need. So if you're making the cut yourself, you get to decide which of the two sides of the line is going to be your set P. You also get to decide where that line is. Now, if you're told you have to have extra criteria, like this one, I was on purpose doing an AZ cut, even though we hadn't had that definition yet. In that case, I'm on purpose chose the side of the line, the cut line here that was arbitrary, that had A in it. I chose this side to be P. But that was just because I wanted this to also be an example of an AZ cut. Depends on the question. So if this is going to be part, if you're going to need this as part of the augmenting flow algorithm, you're going to have an AZ cut. So no, your P would have to be on the left or wherever vertex A is. If all I asked you to find is find a cut of the graph, in that case, yeah, you would get to pick. So just watch out for the directions of whether it asks you to find an AZ cut or just a cut. And that's why I went ahead and put the separate definition of the AZ cut down there. That in your book uses it all the time. All right, so going back to our corollary here is the corollary of Theorem 2 and the first part of it, which is the only part I'm going to write down. So we've got the same upper bound from Theorem 2 that says the value of any flow is less than or equal to the value of any AZ cut, or AZ flow less than or equal to the AZ cut. So here, what does that mean? So if you've got any AZ flow in your network indicated by the F, and you've got any AZ cut indicated by the P comma P complement in your network, it turns out the only time they're going to be equal is if you have the following two criteria. The first criteria says pick any or for all edges E inside of your cut P complement P. Notice that's the reverse, like what we just did. Then the flow going backwards, or the flow going from the side that has the Z on it back to the side that has the A in it, is going to be 0. In other words, don't use backwards edges. It defeats the point of doing the maximum value that you possibly can. And also, for all edges in some AZ cut, where A is in the side of the cut that you're coming from, Z is in the side of the cut you're going to. In this case, the flow has maxed out the capacity. So that would be the idea here. In order for these two guys to be equal, you have to max out your capacity. Now, fair warning here, this one here does talk about any and any. This also can be extrapolated down to a specific flow and a specific cut. If the specific flow is equal to some specific capacity, this would then be true on that one version of your set P and P complement that you're dealing with respect to that specific cut. And in terms of terminology, in this particular case, where you have the value of the flow is equal to the capacity of your cut, what we call them is this flow is the maximum flow. And our cut associated is the minimal cut. So those terminologies, so if somebody says, hey, do you want a maximum flow, or what is the maximum flow, which is what we're going to actually strive towards in this section, what you have to do, you have to max out one of your cuts. All right. Now the rest of the definitions that we have, and we've got a couple of them, are really just the terms that we use in our augmenting flow algorithm. Okay, so this is just like a glossary of the terms that we're going to be using. Most of these guys are totally descriptors. Okay, so don't get overwhelmed by the fact that we've got a lot of terminology in this section. So a unit flow path from vertex A to vertex Z is simply a flow that has a value of 1. That's it. Unit refers to 1 in math. It refers to more than that, but in terms of integers, it refers to 1. So this guy, and we're going to go ahead and call, in terms of symbols, FU, U for unit. This is defined as, if you plug in E, you're going to get back 1. If E is along the path from A to Z, and the flow is going to be 0 if E is not along that path. Okay. Now, the next thing that we're going to need to look at is what are called saturated and unsaturated edges. If you think of this in terms of liquid, sometimes it helps, but you don't have to. A saturated edge is simply an edge, E, where the flow along that edge is at capacity. In other words, if you think in terms of like a sponge that got wet, that sponge, if it's holding as much water as humanly possible, and the more water you add to it will just drip out the other side, that would be its holding as much as possible. In terms of pipes, it's at full capacity. It's totally full of your water that's flowing through. So however you want to think about it. If you're thinking in terms of shipping and trucking, your truck's full. Okay. Now, any guesses what an unsaturated edge is? Yeah, you still got extra stuff that you could push through that edge. It can be where the flow is zero along the edge, and that does happen a lot. But the main thing is you're just not at full capacity yet. Now, when you talk about unsaturated edges, you talk about their slack. Slack is specifically how much extra you could push through an edge. So, only applies to, oh, apparently I just cannot write today, to an unsaturated edge. And this is the slack of some edge E is the total capacity of the edge minus the flow. If the slack is zero, it means you have a saturated edge. Okay. Now, a chain is simply a path in a digraph where you ignore the direction of the arrows. So a path where we ignore the direction of the edges. Now, why do we need to make that distinction? Because if you talk about a path in a digraph or in a directed graph, a path in a digraph is, by default, also called a directed path, which means when you travel from vertex A to vertex G, or vertex A to Z, or B to H, or whatever vertices you go between, as you go through the graph, you have to follow the direction of the edge. And what we're about to do with our algorithm, we're going to say we're not going to bother with the direction of the edge. Now, we're going to have to track it if we go the opposite direction on the edge of what we're supposed to, but in terms of what we're going to be doing is we're actually going to be building chains across our networks. Okay. So the path where you can go backwards on an edge if you want to. Okay. We normally say don't drive the wrong way on a one-way street, but we're going to be doing that sometimes here with our chains. And the last preliminary definition that we need before we actually get into our augmenting flow algorithm is something called a unit flow chain. This is a flow from A to Z that travels along our path from A to Z where we ignore the direction of the edges. Here, the flow along those specific edges on the chain is going to equal 1 if you're on a forward edge. So E is a forward edge, and forward just means you're traveling along the edge in the same direction that you were supposed to. In other words, you travel along the edge in the direction of the directed edge. Now, any guesses when you use the -1? Any guesses when the -1 would happen? +1 was when we traveled along an edge in the same direction as the directed edge. Yep. So the -1 would be when you go along an edge when you go the opposite direction of what you're supposed to. And we are totally going to call it a backwards edge. So we're going in the opposite direction of what we're supposed to on our directed edge. Now, if you look at any edge that is not in the chain, so edges that we didn't care about, not on the path we cared about, those guys are 0 in a unit chain flow. So now we are ready to set up for our augmenting flow algorithm. The augmenting flow algorithm is a beast of an algorithm to actually write down, but in terms of doing the work, once you've done it a couple times, it is a lot of details, but it's actually not as much work as what writing out the algorithm in a descriptive form or in words makes it feel like. Okay, I give you that warning because it is going to feel like a beast. Okay? So what you're given is you're given a network, and you have some initial flow. If you are not given an initial flow, your initial flow is 0 along all edges. Okay? Now, in terms of notations and symbols, there are a couple of symbols that we have to worry about. The first symbol in this algorithm is P. P represents the current vertex that you're scanning from, or as your author calls it, the previous vertex. This is just like in Dijkstra's algorithm, the vertex that currently has a permanent label. It's the one we've already dealt with. So if you prefer, this is somebody with a permanent label. Okay. Now, Q, this is the vertex that we've just scanned to. So this is the vertex that we've just jumped to. Your author calls it the current vertex, and that's actually a perfectly fine way of dealing it. This is the one that we are currently creating the label on that vertex. So in terms of referencing back to something we've already done, if we reference back to Dijkstra's algorithm, P would be like when we go through Dijkstra's algorithm and find the guy with the smallest length path to that point in the graph, and Q would be all of the guys adjacent to him. It turns out that is very analogous to what we're about to do. Then we have this special symbol, and this special symbol right here is the amount of additional flow that we can send through our network at this point. Okay, so this is amount of additional flow that can be sent through chain A to Q. So we don't know that that's how much additional flow that we can push through the entire network, but at this point in our stage of working, this is the amount of additional flow that we can push through at this point in time. Note, this is what you would at first glance think is the slack in that edge, but is in actuality, you have to worry about the slack across the entire chain. So you'd be watching out for how much you can push through all of the edges in the currently built chain. And again, we're going to see how that works in just a second. The formula that we're going to have in just a second here is going to give you a formula that will always calculate this value. Okay, so we will have a specific formula. And it actually looks very similar to the formula we use for Dijkstra's algorithm too. Okay. Now the actual label that we're going to put on each of these vertices when we create their label, it has two components. And the two components go as follows. The second component here is the amount of additional flow that we can push through the network up at least to that vertex. Okay? But the first one is telling you where you came from. So the P part tells you the previous vertex you were on. The plus or the minus tells you whether you followed a backwards or a forwards edge to get there. Okay? So if you started at P previously and you followed a forward edge to get to the current vertex Q, that's a plus. And if you were coming from vertex P previously and to get to Q you followed an edge but in the backwards direction, so in terms of how you progressed, in the same direction of the edge or in the opposite direction of the edge, if you follow the backwards edge, there's where the little negative is. Please note those pluses and minuses totally are coming from this notation right here of your flow along a forward or a backwards edge of the plus or a minus at that point in time. Okay. Now, the rest of this, I don't have fill in the blanks. I'm just going to go through the actual steps. I'm going to go through this relatively quickly with the actual steps because almost everybody who reads it, it has a tendency to not make sense until you actually start doing it. Okay. So the very first thing you do is you initialize your source, your vertex A, with your label. The first part of the label says we didn't come from anywhere else, so I just put a slash through it. And the second part of the label is the additional flow that you could send through the network. Because there's nothing coming previously from the source, we're going to assume we could push as much flow as we want to because we haven't gone through any edges yet. Step 2 is you start scanning from a vertex that already has a label. So if the only guy with a label is the source, you'd start scanning from A. Okay, and it already has the amount of additional flow that you could push through it, which is the second position there. So you initialize at vertex A, or whatever your current vertex is, and at each one of these vertices that you're now looking at, you're going to scan your incoming edges and your outgoing edges, and they're going to be treated differently. So incoming edges, right here, you're going to look at all the edges coming into the vertex P, select all of the vertices going from it, and as long as the flow is greater than 0, we're going to go and check those other vertices that do not currently have labels. You'll change the unlabeled vertex. First part of the new label says we traveled on this edge backwards, and the second part will be additional flow. This additional flow will be the minimum of the previous flow that we were dealing with in our chain, and then the flow along the edge we just traveled. Okay. It does not matter. So the question that came in asked if it matters whether you check incoming or outgoing edges first or second. It doesn't. It just matters that you check them both. So they're independent. You don't have an edge that's both incoming and outgoing, so it doesn't matter the order. I did it here, incoming. If my handout has outgoing first, yep, sorry about that. When I was writing it up, I was thinking incoming first, and I should check with the handout to match it for you guys. Now, the outgoing edges, these are the ones that you normally think of where you're actually doing. So outgoing, well, it depends on your graph whether you have more of which type. You typically think in your head more along the outgoing way. So maybe that's why it got reversed when I was typing it previously, probably. So these are the edges where you follow your directed edges in the correct order of the direction, if you will. So you look for if there's slack along any of those outgoing edges. In other words, you could bump up their capacities, and that you're going to a vertex that's unlabeled. The new label on the unlabeled vertex will say you progressed from vertex P in the forward direction, and then the new actual additional flow would be the minimum of the previous flow we could push through the system, and then the additional flow that you're allowed through that one edge. So this minimum here, right here, is always about, are there any bottlenecks? Are there any edges that aren't allowing you to push as much flow as possible through your system? And because it's labeled flow, I always picture water and pipes in my head with these type of questions, although it's whatever you're actually pushing through the network. So step two is the main step that we're going to repeat, which feels like forever when you progress through your network. Okay, so step 2, this is the big one. Step 1 is just an initialization step. Now, when we jump down here to step 3 says check to see if so that's after you deal with step 2 at whatever edge you're scanning from, so scanning from vertex P. After you do step 2 once, you check to see if vertex Z is labeled, the sink, the place you're trying to get to. If it is, we're going to terminate and go to step 4 as the termination step. If, however, you still have unlabeled vertices in your graph, you're going to choose another labeled vertex to scan from, and we go back to step 2. So like in pseudocode, this would be, your go-to step. Step 3 here, or condition 3, is you still have unlabeled vertices in your graph, but for whatever reason, you can't actually scan from any of your labeled vertices. In other words, the algorithm gets stuck. Okay? So if the algorithm gets stuck before you can actually label vertex Z, what you do is you terminate the algorithm early, and you set P to be the set of labeled vertices. P complement would be your unlabeled vertices, and you're pulling a specific cut. The cut would be P complement, and this is a fully saturated cut, which means you've actually reached a maximum flow at this point. There's no way to tell that you've reached a maximum flow until you get a fully saturated cut. Okay, so this is how you prove that, hey, we already had a maximum flow previously. Now, if we actually do get that vertex Z gets labeled, what that means is we can push more flow through our network. And step 4 tells you what you do. In terms of the actual label on Z, the label on Z, where's the label? The second part here tells you how much additional flow you push through the network. And step 4 shows you how to build an AZ chain K. You basically track labels, and I'll show you how to do that. And those tracked labels are actually going to show you which edges in your originally given flow are going to have their flows either increase where you're going to be able to push more labels through, or decrease if you really shouldn't have put that much flow on that edge and you need to move it to a different edge. Okay? So that is a ton of theory and procedure. This is why I would recommend having that handout next to you when you're working these problems, okay? At least for the first couple of times. So let us start working on an example, and based on the time left, we may or may not be able to finish this example this time. If we don't finish it this time, we'll finish up this example at the beginning of next class. All right? So I'm not going to be able to show you that all the steps of that algorithm as we progress through this. So here goes. So for this one here, we are given an original network. In terms of how to read this network, we have we've got vertices, so we've got 7 vertices total. I went ahead and labeled them A and Z, and let me go ahead and highlight the A and the Z here. We want to start at A and we want to end at Z. Okay? Why? Because A is our source and Z is our sink. The capacities on all of the edges are given by the numbers that are not in parentheses. So this one here is your K of E. And the guys that are inside of the parentheses would be your F of E. Okay? Now, in terms of all of them, so you have both a flow and the capacity associated with everybody here. You also have a direction. The first thing that I would always recommend checking here is your initial flow, specifically the value of your initial flow. Anybody have a guess what the value of the initial flow is? It is. It turns out to be 7. The value of the flow can be checked. I actually like to check the value of the flow either looking at the source or looking at the sink. It's how much is pushed out of the source. This would be 5 plus 2, or how much flow is coming into the sink, which is 6 plus 1. Both situations get you a value of 7. Now, is that flow split up as it progresses through the network? Yep, splits right here at vertex C. So that once you push this, I'm picturing in my head water right here. Once you push this water in at vertex A, it flows through the network however it wants, or however it's currently tagged. And this is our current AZ flow, or the initial AZ flow. Now, when we start, we always start at the source. So we initialize our vertex at P equals A. So A is the source. First, we put a label on A, and the label that you always put on your source is where you came from, nowhere, because we just started, the amount of stuff that we can push through an edge before our source. There's no edge before our source. So at this point, we're going to assume unlimited, and this will obviously be throttled down once we actually get into the capacities on our edges. Okay? So I'm going to go ahead and put this label of dash and then infinity up here on the vertex A. Now, once we have that label, the original label on the source, we scan from this vertex A, and we look at both incoming and outcoming edges. So if you look at vertex A and the edges that are incident to vertex A, do we have any incoming edges? Nope. So we're only going to be looking at outgoing edges. Quite honestly, outgoing edges are ones that we prefer anyway. So in this particular case, our outgoing edges are, and I'm going to be lazy, I really don't want to write the 2-letter name plus curly braces for all of our edges. So let's go ahead and label all of our edges. I'm going to call them E1, E2, etc. E for edge. So here's E1, E2, that was trying to be an E, E3, E4, E5, E6, E7, and E8. So we have a grand total of 8 edges. Nice thing about labeling edges with E and a subscript, you know exactly how many edges you have when you get to the last one. So our outgoing edges here are E1 and E2. So those guys would be like our little Q's. Now, if you have an outgoing edge, you're trying to push additional flow through the edge. Can we push additional flow through both of those two edges? If the answer is no, which edge can we push additional flow through? Right, so to see if you can push additional flow through an edge, you're looking to see if you actually have any slack on the edge. Edge E1 is already maxed out at capacity, so we're not going to be able to push any extra flow through here. However, in terms of E2 right here, our flow is only 2, our capacity is 5, so we actually have some slack going on here. So I'm going to go ahead and cross off E1, and if we only look at E2, the slack on edge E2 is 5 minus 2, so total capacity minus current flow. Then, in terms of the label that is going to be attached to the vertex at the other end of the edge E2, the vertex at the other end of the edge E2 is vertex C. And this is where we use the formula that we had a little bit ago that I'm not expecting you to remember. This one here is the minimum of the additional flow attached to your vertex P right now, so the vertex we're coming from. And since we're trying to push more flow through this edge, our slack. Now, because vertex A was the initialization, this is infinity, and the slack, in other words, the amount of additional flow we can push through that edge E2 is 3, so our final answer here is 3. Notice what that means. This means that our label on vertex C is going to be, well, the new amount of flow we can push through currently is 3. Vertex we came from is A, and then we have to figure out positive or negative. It's going to be positive because we went along the edge in the same direction as the arrow, or as the direction of that edge. So the new label here would be A with a plus and a 3. And then what do? Since we dealt with both of the two edges incident to vertex A, we then scan through all of our vertices, find a vertex that is currently labeled that we haven't dealt with before. So which vertex should we look at next? So this has to be a vertex that is currently labeled but we haven't dealt with before. Currently has a label. So it would have to be C. So if we look at C, it currently has a label. So then we say, so in terms of this guy, let me go ahead and highlight what we just did. We went across this guy. And we're currently now looking at vertex C. If we look at vertex C, we see that there are two edges incident to vertex C. Both of these guys are outgoing edges. I would definitely recommend, at least the first time you do this algorithm, tag your outgoing versus incoming edges and writing it out with all the work like this. As you do this more, you're not going to need to worry about that, or there's shortcut ways of doing it. If we look at our two outgoing edges, we look to see if we can push more flow along either of those two edges. Can we push more flow along both of those two edges? And if the answer is no, which of those two edges can we put more flow on? Right, E6 is currently maxed out, so it has no more flow to handle. Can we put more flow on E5? Yes. So we'll cross off E6, and we're only going to be then looking at edge E5. So if we look at edge E5, it's an outgoing edge, so we look at slack. So how much additional flow could we push through edge E5? Did not mean to do that for you guys. Sorry about that. 2? Yep, 3 minus 1, or 2. So then we're going to calculate, and you actually don't have to look at the graph for this one. We're going to calculate the label that is going to be attached to the other end of E5, which is going to be the vertex E. I wish I had not picked the symbol E for a vertex label at this point, but Oh dear, it happened. So this is going to be the minimum of the label that we're coming from. So this is the label on C, and the slack on the edge E5. Okay? So we already found the maximum flow that we could push through to vertex C. It was 3. Notice I'm actually pulling it from right up here or right there, as opposed to looking at the graph, although we could actually still see it on the graph. And the slack we just found, which was 2. So what's our answer for that label on vertex E? Or at least the change in vertex E, or the additional flow on vertex E. Yep. Coming from C, we went on a forward arrow, and that answer here, the number of minimum of 3 and 2, is a 2. So now we'll put that label back on our actual graph. Stop moving like that. So this guy is coming from C. And we have 2. Okay. At this point, so that terminates that sort of looping of checking vertices. So then we check all of our vertices again, and we check vertices that have labels. This is the key. The vertex has to already have a label. So of the vertices that already have a label, who have we not scanned from yet? Only vertex E. Notice the only time you have actually a choice of more than one vertex is if maybe something like edge E6 here hadn't been maxed out at capacity. In that case, we would have labeled both of these vertices in that last sweep. So now we're going to be looking at vertex E. Now, vertex E is the first time that we have edges that are both incoming and outgoing. Okay? In terms of the incoming and outgoing edges, I on purpose labeled these edges here. We've actually already dealt with edge E5, so it's going to turn out it won't be one that we need to use here, but let's go ahead and check it anyway. All right. So our next vertex that we're going to scan from is vertex E. We have both incoming and outgoing edges. So incoming. Now, I know you can't see the picture, but if anybody has the graph in front of them, did anybody spot the incoming edge? As I scroll that back down. Anybody spot the incoming edge? It is only E3. Well, technically it's E5 as well. So let's write down both of them. So E3 and E5. Now, in our algorithm, when we look at these guys, what do we have to have? We have to have a you have to have 2 things. You have to have both that you're going to when you travel on your edge, you have to go back to a vertex that's unlabeled, and you also have to have flow along the edge. So looking only at these 2 incoming edges, notice we already have a label on the other end of E5, so that one you're not going to use if there's a label on the other end. Now for the other guy, edge E3, there's not a label back on vertex B, so E3 is somebody that's potentially in play. Then you check, is there any flow currently on E3? And the answer here is yes. For this particular example, the flow was 5, but it also would be true if the flow was maxed out. It is okay to, if you're going in the backwards direction, if the flow is completely maxed out, you'd still be dealing with that particular edge. The only thing you can't do on a backward edge is you can't deal with it if it doesn't have any flow. Why? Because on backwards edges, what we're going to be doing is we're going to be removing current flow from that edge and putting it somewhere else in the network. Okay? So you must have positive flow on a backwards edge or an incoming edge. So E5 had an endpoint that was already labeled, and if we look at E3, the flow along E3 was 5. It was the number that was inside that parenthesis that we saw a second ago. This guy is positive, so that means we are going to use edge E3. Just a second. So the question coming in was looking at E1. Ooh, that is a good question. Well, right now, E1, we're not dealing with in a backward sense. So back when we would have looked at E1 is when we were coming from the source. And in that case, if this guy had been a 4 instead of a 5, you would have actually added extra flow to both of them. So in our case so far, we've only been dealing with one edge at a time. And what we're about to do, we're still only going to deal with one edge at a time. But if you do have multiple guys where you could either add flow or subtract flow from the edge, you do them all when you're scanning from that one vertex. So if this one wasn't maxed out. I on purpose did this example because it's a relatively straightforward example. But in retrospect, it probably should have made the flow less, so we could actually see that we would have needed to adjust both of those two edges at the first iteration right here. In that case, you would not have crossed off E1, and you would have calculated the label both on B and at C in that first pass, or the first scan. Where were we? Right, so we're looking at E3. We just calculated that the flow was 5. We pulled it directly from the inside of the parentheses. That flow is bigger than 0, so we are going to calculate a label on E3. Edge E3 goes back to B, so we'll look at the minimum of the label that's currently on the edge we scanned from. So on the vertex we scanned from, so that's vertex E. And watch out, we're dealing with an incoming edge, so the formula for an incoming edge is you don't take the minimum of slack versus the previous label. It's the minimum of the previous label and the flow. So let me underline this. Incoming edge, you changed up your formula. Okay. Now, when we plug this in, the label on the previous vertex was 2, and then the flow that we had here was 5, so the minimum value of 2 and 5, hopefully you're all thinking, is 2. Now, any guesses what the label on that vertex B would end up being? Well, the amount of flow that we could deal with here is 2. And since it's an incoming edge, we traveled the opposite direction of the edge that we should have, so we're going to have a little minus up there. Okay? And that would be the label. So I'm going to go and put this label actually in the picture on the graph. So we came from E backwards of how we should have, and the amount of flow that we're trying to push through the system is still 2. Now, we've taken care of incoming edges. Now, if we look at outgoing edges, can we push any additional flow on the only outgoing edge from vertex E? What do you guys think? Can we push any additional flow on this outgoing edge E7? No, it's already at max capacity. So if we write that down, if we say outgoing edges, the only outgoing edges was E7, cross it off because it's already maxed out its capacity, which means we're done scanning from vertex E and putting new labels. We only ended up with one new label. So going back to the picture, we look for a vertex that currently has a label but hasn't been scanned from yet. So do we have any vertices that have a label but has not been scanned from yet? Sorry about that. Yep, B. Now, I'm going to go ahead and color code this one, highlight it again, but I'm on purpose highlighting it blue instead of yellow, and that's to indicate that we went in the opposite direction of the direction of the arrow. It's the first time we've gone in the opposite direction. So now our P is going to be B, so the current vertex we're scanning from is B. In terms of vertex B, there are both incoming and outgoing edges. So the incoming edge, we'll go ahead and tag these guys, and then we'll write it down. Outgoing. So incoming edge, there's 1, E1. Outgoing edges, there's 2, E3 we just traveled on, and E4. Now remember, you can only use an edge if first and foremost the opposite endpoint of the edge is unlabeled. Do we have any of these edges that have the opposite endpoint or the endpoint on the other end of the edge unlabeled? If so, which one? Yes, that works. So this one here, B to D, E3 we've already used. E1 we can't use because its other endpoint is somebody who's labeled, so we're only going to be able to look at E4, which is an outgoing edge. Okay? So if we go down here and label this, incoming edges was E1, but we can't use it because it's labeled on the other edge. Endpoint E3 and E4. E3 we can't use because we've already dealt with the endpoint as well. So if we look at E3, it's an E4, excuse me, it's an outgoing edge, so that means we're going to be looking at slack, and then we're going to calculate the label on its endpoint, which is D. So let's go back up to the picture. So focusing here on E4, anybody got what the slack is on that edge E4 from vertex B to D? Yep, the slack is totally 3, and that is sufficient to calculate the label on D. The slack here is 3, which means we have the minimum of the previous label, which is 2, the slack, which is 3, and that minimum is 2, which means the new label, and this is the label on D, is going to be we came from B in the forward direction, and we still can push 2 extra units of flow through. So here, we came from B in the forward direction, push 2 units of flow through. And I'm going to go ahead and highlight the edge we just used because on D is the only vertex right now that has a label we haven't scanned from yet. Now, we'll then scan from vertex D. The only vertex that's unlabeled left in the whole network is Z, so we have to only go D to Z. And we can actually do this in the actual graph. And this is why I say that this algorithm, while it seems intense if you write out all the details, you can actually do it in the graph really quickly. Notice the label here is going to be what? First part of the label is we're going to be going from D. This edge, E8, is in the forward direction, which means we're pushing additional flow through. So currently, we're only allowed to push an additional 2 units of flow through. So any guesses, can we actually push all 2 of those units of flow through here? Yeah, we can, which means we did the minimum of the slack, which is 5, and 2, which is the previous label, so that minimum is 2. Now, at this point, you have a label on vertex Z. What does that tell you? This label right there, that 2, tells you the amount of additional flow you can add to the system. So let's close out this question. And I'll write in after class the additional details on what we would have done on D, same as what we did before, but since it was the same as before, I'm going to leave a blank there for right now for us. So what we just got was the label on Z, D plus and 2. So our new value of our flow is going to be the value of the previous flow plus the label on Z, and that is always true. In our case, previously, we found that the initial flow was 7. Add that 2, which means the new value of the flow is 9. Now, this doesn't yet tell you how to adjust your flow. Here's what you do. So to adjust the actual flow values, your forward edges, you're going to take the current value of the flow on the edge and add that new value to it. Any guesses what we're going to do on the backwards edges, the ones where we went in the opposite direction? Going to subtract. So your new flow goes as follows. Only on the highlighted edges. So let me go ahead and make this back in black. Here, your flow is not 2, but 4. Over here on the highlighted edge, not 1, but 3. I'm adding 2 each time. Here, highlighted edge, add 2. Here, highlighted edge, add 2, so you're now 3. Now the blue highlighted edge was backwards, so we're going to subtract. Now, why would we subtract? Notice total flow going in here was 5. So if you split and now have flow of 2 units go B to D, you have to reduce the total of 5 over there. So this one is going to be reduced by 2 units in a new flow of 3. Okay. Notice at each one of these junction points, you still have to have the total flow in be the same as the total flow out. And that's why you have this. Normally you're adding everywhere, but over here we actually had to subtract. Okay. And that's how to adjust the flow. Now, we've done basically everything with the augmenting flow algorithm. The only thing we didn't get to is how to verify if this is a maximum flow or not. So next time, we'll look at this exact same example, and we'll see how to tell if we've actually achieved a maximum flow. If we haven't achieved a maximum flow, you get to do all of this work a second time to get a second new flow, and then you check to see if it's a maximum flow. Okay. That's your augmenting flow algorithm. That is it for today.